The definition of I is integral r squared dm, but it also has a summation version, just like center of mass did. A summation of r sub I squared m sub I. Remember, that's what we began the lecture. Just like center of mass has a summation version, and it has a integral version. So I'll show you both cases. So its units are going to be units of mass times distance squared. So it's going to be kilogram times meter squared, or slug times feet squared, or any other units of mass times distance squared. So it's going to carry the same meaning as mass in linear case. It's going to tell you how hard it is to rotate something, okay? So if you have just a point object, this is the simplest case. Let's say you have a string, and it's being rotated around the end, and let's say the string doesn't weigh anything. So let's say you have a m, and this is d. What's the moment of inertia of that mass rotating around that point? This is the simplest moment of inertia you can have, okay? So its moment of inertia is going to be, it's rotating this way, right? So md squared, right? Okay, now we get a little harder now as we go. I'm going to add more stuff. What if the string is like that, with a mass m, another mass m, another distance d away? What's the total moment of inertia of those two objects around that point? And I could keep adding objects like this, you know. So the total moment of inertia, this is the one where we use summation, you see. So it would be m times d squared plus that mass times its distance from that point squared, you see. So it would be here. What is its distance from that point? 2d, right? So it'll be, let's see here. They're both same mass, m. Yeah. So md squared plus m times its distance is 2. So what is that? 4 plus 1, that's 5, right? So that means it is 5 times harder to rotate this around that point than it is to rotate this around that point. This one is 5 times harder because you have this mass distributed twice as far away. So the farther it is away, the harder it is to turn, you see. So